Example problem number 1 states, what is the capacitance of an oscillating LC circuit in nanofarads if the maximum charge on the capacitor is 2.15 microcoulombs and the energy is 208 microjoules? So we know that UB plus UC, which is basically the potential in the inductor plus the potential in the capacitor at any given time, is equal to Q max squared divided by 2C. So we know that whenever we're dealing with this, we have Q max squared divided by 2C is going to be equal to 208 microjoules, because that is going to be the total energy at any point, whether it's over the inductor and the capacitor at either their maxima or any time in between. So we know what Q max is, so it's 2.15 e to the negative 6 squared divided by 2C, and then we set that equal to 208 e minus 6 joules. So by plugging and chugging, we get a capacitance of 11.1 e to the negative 9 farads, so 11.1 nanofarads. So example problem number 2 states, in an oscillating LC circuit, we have an inductance of 0.898 millihenries and a capacitance of 5.35 microfarads. The maximum charge of the capacitor is 3.49 microcoulombs. Find the maximum current. So here we can say that our inductance plus our capacitance is again equal to Q max at any time. So whenever we have the maximum current, we do not have any energy in the capacitor. So we have 1/2 Li squared is equal to Q max squared divided by 2C. So we have our maximum current is equal to Q max squared divided by L times C. And so now we can plug in these numbers and then chug it through our calculator, so we can actually solve for the maximum current in the inductor. So whenever we have the maximum current, we only have energy in the inductor and no energy going through the capacitor at that time. So we're in the max current case. And so we're going to plug in these values, and then we get a current that is going to be equal to 0.0504 amps. So that is the maximum current in the inductor. So in an oscillating LC circuit with an inductance of 72 millihenries and a capacitance of 5.3 microfarads, the current is initially at a maximum. So how long will it take before the capacitor is fully charged for the first time? So whenever we're at a maximum, we're altering our diagram a little bit. So whenever we have a current that's at our maximum, we have the maximum potential energy going through the inductor. So we know whenever we have the cycle, we start off with the maximum current going through the inductor, and then we're going to have the maximum current moving through the capacitor, and it's going to be have a current the same direction as the original current, and then we're going to have the maximum charge on the inductor only in the opposite way that it was previously, and then the maximum charge over the capacitor. So we're really just looking for the time it takes to get through 1/4 of the cycle here, since we're looking at the transfer between the maximum potential energy to the maximum capacitance. So then we have our time is equal to the time it takes to complete one cycle divided by 4, since we're only interested in 1/4 of the cycle. So how long will it take? So we know that our T is going to be equal to 1 divided by F, and we know that omega is equal to 2 pi F. So we can say that F is equal to omega divided by 2 pi. And then we plug that in for 1 divided by F. So we have 1 divided by omega divided by 2 pi. So then we can move 2 pi to the numerator. And then we have omega in the denominator. And so omega is equal to 1 divided by LC to the square root. And then we know that our period is going to be 2 pi times the square root of L times C. And so we now can just plug in our values, because we know that the time it takes is equal to the period divided by 4. So we have our period divided by 4, plug in the values for the inductance, plug in the values for the capacitance, plug everything into our calculator, and we get a final value. And our final value is 9.7 e to the negative 4 seconds. So our last problem focuses on the RLC circuit. So we have an oscillating series RLC circuit with a 9.01 ohm resistor, a 14.8 Henry inductor, and we find the time required to find the maximum energy present in the capacitor during an oscillation half of its initial value. So we are saying that we're at the maximum energy. So since we're at the maximum energy, we don't have a phase angle. So we can kind of look at it through there. So now we have to think about the setup of this problem, which is a little bit more complex than it normally is. If we only had an inductor and a capacitor, we can say that our maximum energy is just going to be equal to the potential over the inductor plus the potential over the capacitor at any given time. But since we have our resistor, we have to think about the damping of the circuit. And so now we have to think about how we can relate this to Q max divided by 2C. So Q max divided by 2C is our maximum potential energy of an LC circuit. So if we pretend that at time is equal to 0, we're at maximum energy, so we don't have any damping, that means that our exponential function just goes to 1. So then we basically are left with Q max divided by 2C. So now let's relate our Q max whenever we do have damping to our Q max whenever we have essentially our RLC circuit. So then we have it's equal to